Yeah, but like relative to like a test.
What's that?
Yeah. All right. So what I passed out was like the past 2 years worth of test questions.
Wow.
We're not going to go through it all today. No.
Are we getting there?
So,
Studying how the wording.
it varies. But so, I mean, depending on how long it
I'm not even getting this.
there is almost always a problem like this because part of what we use this course to evaluate is your knowledge of differential equations.
Director of Special Product.
And so this one I'm asking you to solve the way you would do it in differential equations. Now in this course, don't freak out.
Sorry.
It says x is equal to x e to the s t, not lambda t, I think, right? In this book, or did I? Hopefully that, but you don't use lambda. And so if I would do it, if I remember this, it should make you the st. But it's, you got a problem like this on the homework. And so are we good at this, or do we need to review? A quick review. All right, so assume solution of that. What does that help us with? Derivative. So we have x equals magnitude e to the st x dot looks like that's what we have our derivatives. And now we can plug our derivatives into our original equation, and we'll do our substitution of our mass as well. So we get 3s squared x e to the st plus 18s x e to the st plus 27. What's the next one? X e to the st equals 0, and then look, we have common stuff. So we end up with, we can pull out a 3, so it's 3s squared plus 6s plus 9 x e to the st equals 0. And how can this be equal to 0? If x equals 0 is the easy solution, that is, it doesn't move, and so it solves the differential equations. But that doesn't, or basically this term has to equal 0. So basically we get s equals what? So s plus 3 squared equals 0. So this gives us a repeated or double root. And whenever we have a root, then we basically get x of t is equal to what's the form? In some magnitude, e to the minus 3t plus some other magnitude, t e to the minus 3. So double root gives you this solution. And then what do we do with this? So x of 0 is given to be 1, and that's equal to, plug into 0, we get a. Take the derivative. Uh-oh, we have to do calculus. Oh no, so it's minus 3a e to the minus 3t plus b e to the minus 3t minus 3bt e to the minus 3t. Where did I Got my product rule right? So it's the derivative of this times this plus this times the derivative of that. And so x dot of 0 is given to be 5 is equal to minus 3 times a is 1 plus b, so that tells us b equals 8. And so what is the solution? So x of t equals, a is 1, and so it's e to the minus 3t plus 8t e to the minus 3t. Now what if we had s equals 3 plus or minus 4j? What's x of t equal to? It's a sine cosine. It's sine cosine, and so it's what? Sorry. Let's make it stable, so it's minus 3. So then it would be e to the minus 3t. The real part is e to the minus 3t. Then we would have a sine of 4t plus b cosine 4t. So whenever you have complex conjugates, so again, you assume a solution, plug it in, factor out this is equal to 0. That is your eigenvalue equation. That's the one frequency we can do. And then based on the roots, repeated roots, it looks like this. Complex conjugate roots, it looks like this. What if we had, and then you would take the derivative of this to get basically initial conditions. What happens if s equals 2, negative 2, negative 5? Then we would have x of t equals a e to the minus 2t plus b e to the minus 5t. So this one is the simplest in terms of the calculus, but you end up with 2 equations and 2 unknowns. So a and b. So hopefully it'll be simple enough. Well, this one is a plus b. The other one, x dot of t is equal to minus 2a minus 5b. So if you just add 2 times this, you can cancel out the a. So if you have nice round numbers, this isn't too bad. If you have like 2.73234 and 5.27128, assuming it is 2 and 5, we'll go with that. Anyway, so that's basically the 3 types of solutions. So you basically solve for the coefficients, and then you write down what the answer is. So this is review. You should have learned this in differential equations. Yes?
So what did you write on the left-hand side underneath the x dot double dot? I
Here?
didn't follow, yeah, I didn't follow where it.
So this, if this was your roots, then this is what your x looks like.
Roots of what? Oh,
Different characteristics.
Here's our characteristic equation.
but it's a different one.
It's a different one. If perhaps when you did the math, you would end up with complex conjugate,
Gotcha,
and the solution
instead,
looks like this.
okay, instead of just
If
the-
perhaps you did the math, these are your
two
two
different.
real roots, then your math looks like
Okay,
that.
okay.
So this is the only one that is more challenging to do calculus. But again, the derivatives are in your notes. If you got your notes. So that's, what? I could.
Hey, that's an easy one. Do it. Put it on there. I dare you.
We've learned this like 20 times every class.
It's done by now, you know.
100 times.
Like, again, this is easy, but what is this when t is equal to 0? This is 1, this is 0, and so basically what we get is b is equal to whatever x0 is. So in terms of solving for a and b, this is fairly easy. And the derivative of this should be in your notes, which you can just copy down. That's so basically when I say assume solution of this, I'm saying I'm using this to check to see if you still know differential equations or finally learned it after your third time experiencing it. Is it third or fourth? Don't say first.
Not enough.
Not enough. All right. All right, these are more touchy-feely type problems. All right. So it's basically, do you understand basic concepts? And so, number 2, they all have the same values as C and M, but have different values of K. Order the plots from smallest to largest values of K. Explain your reasoning. So what changes your response? We have damping, so we have our zeta, and we also have omega n. What's your zeta equal to in terms of Kc and
C over 2 root Kf.
very good. And omega n is
Root K over F.
all right. So those are your 2 things. And so basically, as we want to smallest to largest, so as K goes up, what happens to our squiggle zeta goes down, which means what?
More overshoot.
More overshoot,
And quicker response.
longer to decay. So basically, you're going to get more overshoot, you're going to get more wiggles before we die out. And this, as K goes up, omega n goes up, what does that do to our response? Speed. So basically, we're going to be faster. And so the slowest response has the lowest K, which is the slowest response. Number 1, next slowest, 3, and then 4. And so basically, that's the solution. Okay. So I don't think the numbers were there when I actually gave you the test. I copied this from the solution to the test. You'll have a different question. So it's basically one has the slowest response. So as the numbers, as we get bigger, it gets faster and it gets wigglier. And so you could use either the wiggly argument or the faster argument. Not the cheaper argument, but faster, better, cheaper, argument 2. All right, so that's basically that. All right, so hey, similar problem, except now what do we have? We have same C and K, different values of M. And so here, for our squiggle, as M goes up, what happens to our damping? Our damping goes down, which means we're going to get more overshoot, longer to decay, so more wiggles, more overshoot. And basically, as for omega n, as M goes up, omega n goes down, and so therefore this is slower. All right, so which color is the smallest value of M? Green. So this is 1, 2, 3, 4. So as mass increases, damping goes down, so we're going to get more wiggles. So the red has the most wiggles, so it has the most mass. And the green, lime green, has the least wiggles, so it has the least mass. And then as mass increases, it's slower to get to the peak, and so you get the same answer. Amazing. All right, we have a car suspension system. What type of vibrations problem is the car suspension system?
Base motion.
Base motion. Right, so the ground moves relative to the ground is going up and down, so it's going to give base motion. What is the purpose of the spring? No. What's the purpose of the spring?
Limit deflection.
Limits deflection, absorbs forces, gives you your steady state force. So the spring sort of cushions the response. And then what's the damper? To stop the oscillations. So basically, the damper is going to take the energy off the system, so you're not going to oscillate forever. The spring is what's cushioning the road motion. Typically, you want to operate this above or below the natural frequency.
If you want a smooth ride, you want it above.
If you want a smooth ride, you want it above.
If you want less force, you go below.
Yeah. So if you drive really slowly, you get low force. But basically above. Remember the base motion problem looked like that. So at high frequencies, you're going to get little amplitude. So you want to be above your natural. If you want small vertical deflection, yes. Unless you get conk and then something falls out of your car.
It works.
They do it so then you can like launch people out of the back seat.
We read that.
Yeah, the bus too. Not the one to boards, but just like the track meet. Okay.
Well, they're all born.
They're all the same bus. All right. So why don't we include gravity? Usually.
Because it's at equilibrium.
Because at equilibrium. So at equilibrium, your spring force is going to cancel out your gravity force. So we neglect it when we're drawing our free body diagrams. When do we need to include gravity? Pendulum. Whenever gravity restores in both directions like pendulums, we need to include it, or inverted pendulums. All right, for a washing machine, what causes the vibration? What type of problem is it? Rotating imbalance. And then they put concrete on the bottom, or concrete, where's the cement? Where's cement? Oh, my arrows somehow, I don't know, is that? I guess somewhere there's cement. So what's the purpose of adding cement? Increases your mass. Remember your amplitude was ME over M. Big M X over little m. Something like that.
Is it big M over small m? Or little m over big M? I think it's not.
That's why it's an open book test. This is so basically, as big M goes up, X goes down for the same amount of imbalance. What's the purpose of the springs? Cushions. You don't want to shake the house, usually. What's the purpose of the damper? Absorb some energy. What else? The damper.
It helps to
Lowers the amplitude, yeah.
Yeah, it keeps it from what's it called when it scrapes or
Tough strike.
tough strike. Does it reduce?
So
that?
basically, as you're going to speed up or slow down, you're going to pass through resonance. So to keep the infinite magnitude of resonance, you have a little bit of damping, and then you try your best to go through it quickly. But yeah, so the purpose of the damper is to limit the resonant peak. But once we get above resonance, the damper is actually not helping us.
Question.
Yes?
I missed your official explanation of A.
A?
Yeah, I know it's like, because you account for
A?
it in your initial deflection, right?
Okay, so the one upper right-hand corner?
Yeah.
Basically, you're at equilibrium, so the spring force is going to be opposite gravity. And so you would use gravity to find your equilibrium position, but once you write your equations about equilibrium,
It's our operating point.
it's your operating point, so the spring forces canceling
And
gravity.
that's a good explanation for this.
Yeah.
And then could you explain springs one more time on the washing machine?
It's going to cushion it so that the vibration here is transferred to the base through the springs. And so it basically, it reduces the vibrations transferred to the base. So it's vibration isolation. So we don't want to keep people from getting sick. You want to decay, after you go over the bump, you want to decay. And not something else. Unless you're in a bus and you want to go through your cabin. What? Yeah. All right. So this is from last year. What type of damping do we have? Under?
Under dam.
No.
No, ooh, Coulomb dam.
Friction.
It's definitely Coulomb.
What type of friction? Dry friction, Coulomb friction. How do we know that?
It's linear.
No, this is just the oily surface. We could get viscous damping as well.
Because it just kind of stops after the water.
So it kind of stops, not at equilibrium, and it has a linear slope going down.
Oh, yes, it does.
So it's Coulomb, dry friction. So now if we listen to our signal, what do we find out? So what do we know about our signal? Oscillates at what frequency? Omega's a good start. It stops, it oscillates at omega n. And what we find is that our period is 0.6, and so omega n is 2 pi over, I guess this should be tau if we want to. So, what is it? I didn't write it down. I didn't write it down. Yeah. Oh, we want to determine the spring stiffness. So basically, omega n is equal to the square root of k over m. To make life easier, mass is 1, so k equals omega n squared. So it's 2 pi over tau squared. And that is 109.67 newtons per meter, but that's ridiculous. Because that's a lot of significant digits for something you're reading off of a chart. So if it was a real problem, your 0.6 wouldn't be that accurate. It's a fake test solution problem where the numbers line up. So now we know what our K is. What about dry friction? So basically, from dry friction, you get your decay per cycle. And that is 4 mu n over k. What's our decay per cycle? Looking at the plot,
Alright, second one,
0.15. Where do we get that? Well, we start at 4, 2 cycles later we're at 1. So in 2 cycles we go down 0.3. So in 1 cycle we go down 0.15. And so from here we get mu equals 0.15 times RK is 110.6. Over 4n. What is n? 1.81. And therefore we get 0.4.
What does n stand for?
N is the normal force.
Okay.
And since my pretty picture says it's horizontal, then the normal force is going to be 1 times g.
Where'd you find the 0.15?
0.15. So decay per cycle. So in 1 cycle, we go from 0.4 down to 2.5.
Okay.
Sorry, 0.25. That's. And then it's easier to see here. Now we're actually down to 2. So in 2 cycles, we're going down 0.3. So in 1 cycle, it is 1.5. Or we could go from here to there, but that's ugly. And then once we hit here, we're going to stop. Why are we stopping?
Friction.
Friction. So basically, the restoring force from the spring is smaller than the friction force, causing us to stay put.
So, a non-dry friction would not have a linear dependent order, it would end at 0.
Speaking of non-dry friction, yes. So this is a non-dry friction. So what type of damping is this? What's left? Is it hysteretic or viscous? And we can't tell. Just by looking at a plot, we can't tell. So basically, hysteretic, how would we know if we have hysteretic damping?
If there's
What causes hysteretic damping?
deflection, or like
Molecules, so it's basically like a cantilever beam or things like that. If there's no other damping and it's decaying, it's hysteretic. But otherwise, it's probably viscous type damping. And so with viscous type damping, how do we get our equations? How do we identify what's going on?
Omega D equals.
So basically, we have omega d equals omega n square root of 1 minus zeta squared. And that's 2 pi over tau d. What's tau d?
Period.
The period, yeah.
3.
Which in this case is 3, 6, yeah, so it's 3. It looks like 35. So that's how we need to find either omega n or zeta. We need another equation. How do we find one of the other two things? Log decrement. So our log decrement is the natural log of x0 over x1. So what did we have? X0 is what? No, it's not 19. No? No? 19 is on the right track, but it's slightly off.
13.
18, that's just, count down.
14.
So X, 19 is the right point to be looking at, but what is the amplitude?
14.
Oh.
No.
9.5.
9, why is the amplitude 9?
Because it's equilibrium at 10.
So again, amplitude is from equilibrium. And so our equilibrium is at 10. And so x1 is the amplitude above equilibrium, which is 19 minus 10, which is 9. So this is your, and this is, oh, did I mess this up? I probably messed this up. And this is in
Tricky, Dr. Heckman.
centimeters. It is tricky. But that year when we did actual position rather than acceleration, I guess even with acceleration we have an offset depending on which way the sensor is pointing. All right, so then x1 is
3.
3. So it's 13 minus 10, 3 centimeters. And so, actually it doesn't matter. So this is 9 over 3. So I thought it was meters, but it's actually centimeters. But that really doesn't matter because it cancels itself out. So this is 1 point, where'd it go? It's a 1.0986 because that's a lot of sig figs. So
1.1.
what? 1.01? So therefore our squiggle is what? 1.1. 1 point, yeah, I like 1.1 better. Yeah. So basically for small values of damping or delta, it's delta over 2 pi. And so it's 1.1 over 2 times pi, which is 0.175. So omega d is,
What do you consider small?
what do I consider small? Whatever we said on the chart. Oh, that always messes me up.
0.2.
It's not chapter 3. Yep.
Wait, it is. Yeah, so that's what I'm just looking at. I couldn't find that. That's what
So here's your equations. So for delta 2 or less, right?
And for damping, 0.3.
So damping of 0.3 or less. But again, we're calculating delta first. So basically, 1 is less than 2. So we can,
Or we could just plug it in.
read it off. Not cheaters. Is this a Pokestop? I wish. Or what was it, a gym? If it was a gym, no one could anywhere. I'm not that quick today. Anyway, so again, log decrement, you go here. If you have multiple, you can use multiple, and go there. But again, since this was an obvious test question, all the numbers were accurate, ridiculously,
Yeah, I'm trying to find where that is in the book.
So 2 pi
I'm
over
trying to find that.
3, so that's 2.094. So omega n is omega d 1 minus zeta squared. So 2.094 over 1 minus 0.175 squared square root is 2.13 radians per second. Are we done? What was the question? All right, so we found natural frequency and damping ratio. And now we're given a force.
Oh, yeah.
And we want to find so we have a force and a magnitude. What is the expected amplitude of the system? Now we're in what chapter? Chapter 3. 1 through 3, yeah. So we basically, the magnitude is equal to either F over that's one of the forms. The other form is X over delta static is 1 over that. Which do we want to use? Sorry, I didn't make it a clicker question. One on the right. Why? We don't have K or C, but we basically can find R, and we have zeta. We can find R. Delta static is what? It's F naught over K. But we don't have K. We have a delta. This is log decrement delta, which is completely different than delta static. This is a dimensionless ratio. This is a distance. And so we have to find K. How can we find K?
Natural frequency.
Natural frequency. So basically we have omega n. So basically omega n is square root of K over m. And so basically what we get is K equals omega n squared m, which is 2.13 squared times 1. What? Mass is 1 kg. Just to make life easy. No, that's if you have no idea what you're doing. Then, if you have no idea how to find omega n and or k, then you can say, hey, well, at least we can solve this, even if we were completely lost. So, if you have no given the test, you have no idea how to do this. And then you say, okay, I will use this. And later on you say, oh, that's log decrement, and you solve it here. You don't have to resolve it. Right? It's not double jeopardy. It's like, oh, so ideally you would solve it in order and it would make sense. These are obviously made up numbers. But at least it gives you something to work with. Hopefully your numbers here are a little simpler, but maybe not. Anyways, so that's your K is 5 to 5 per meter And then what's R going to be?
A ratio.
Omega over omega n. So omega is, this is the other tricky part, 60, what? Yeah, times 2 pi. Again, this is 60 cycles per second, 2 pi in a cycle. So I'm checking to see, hey, do you know how to convert between hertz and omegas and radians, not frequency, and omega n? 2.13. And so that is 177. Do we expect a large amplitude? No. Okay, why not? We're way, way, way over resonance. So we're down in the negligible region. So now we can basically come up to here, plug in numbers. And so delta static F naught, 100 newtons. K we found was 4.5 newtons per meter. So we're basically bringing delta static over. So this is delta static over 1 minus 177 squared plus 2 times our zeta, 0.175. Times 177 squared. The square root is 0.00704.
That's all for what? Delta static or that's not? Oh no, that's the static.
So this is x. So this term here was delta static, F naught over. Okay, so I basically moved delta static up here. Solve for the arrows sort of don't make sense. So again, force vibration. What? Open book, open note. You're not supposed to memorize lots of stuff. Okay, it is an open book, open note test. Does this mean you have time during the test to study?
Yes.
Probably not. It's an hour and a half. It's like, so whenever you approach an open book, open note, what do? Kind of flip through the, make a formula sheet. Pretend it's a closed book test. You have your formula sheet where you have everything you need to know all in one place. Because there's lots of other places in your notes where things could be. So I would approach, typically write your formula sheet. If I get wacky and do something you weren't expecting, at least you have your notes to refer to.
Don't get wet.
Don't get wacky. Well, so it depends on what you're expecting. And so, I also don't get a very bad score. So, anyways. Freebie stuff.
Chapter 1.
Chapter 1.
You have to find the
So all I had to do was a little cloth part pop
This
off
good stuff?
somewhere. I don't know where.
It's like reading.
So now I'm just gonna hold up. That's what I look for.
All right, so
Wouldn't have prompts for it.
how can we solve this problem?
equivalent mass and
So I like M equivalent and K equivalent because then we don't have to deal with moments We could take the sum of the moments around this point here. Because, why do we take sum of the moments about here?
Zero.
Not the center of rotation. Where your reaction forces go away. So if we take some of the moments about the point of contact and ground, then our horizontal and vertical forces are not there. And we end up with one equation and one of those, which is easier to solve. Or we could find M equivalent, K equivalent. And so to find M equivalent, what do we have? So basically our kinetic energy is 1/2 M equivalent times what? What variable do we want to use? X, CG, dot?
Which CG is
The center? Is X dot squared? Yeah. That's the center of gravity. Is equal to what? 1/2 M XCG dot squared plus. Whenever we have a mass, we ask ourselves two things. Does the center move? If the center moves, we have a 1/2 M velocity of the center of gravity squared. And then we ask, does it roll or rotate?
Yeah.
And so then we have
1/2 J omega.
1/2 JCG theta dot squared. And then we need a way to relate theta and XCG.
Do we need two of those for each disk, or could we?
Now the system has
Center.
3 disks together, has a JCG combined.
X equal theta R.
So X
Does.
equals R theta, very good.
The little R, right?
And so R is by definition the distance between the point of interest and
Rotation.
the center of rotation. So the point of interest is the center of gravity. The point of no motion is
That
In this
flat surface.
the ground. So we're assuming we're rolling without slipping. R is the distance between the point where that's not moving and the center of gravity. And so that is, so basically we get theta is X over what's R? No. Yes. 10. What units are we doing? Centimeters. So 10 centimeters. And so we can plug things in. So it's 1/2 M XCG dot squared plus 1/2 JCG times XCG dot over 10 centimeters is 0.01 meters. 0.1 meters? 10? And so, hey, now we're happy. Why are we happy? 1/2 cancels, XCG cancels, and so basically we get M equivalent is equal to M plus 100 JCG. Does that work?
Dr. Heckman?
Yes.
So in the top right we have theta.
Uh-huh.
Theta dot though, right? For J, theta dot. Ah.
Okay. Take the derivative of both sides. All right, so that is M equivalent. What about K equivalent? What, sir? What? So but this is a relationship between x and theta. We could also use it between theta dot and theta. What is the point? All the other stuff. All right, potential energy is 1/2 K equivalent x Cg squared. And again, we have to use the same variable in the equivalence to make it fair. And it's equal to 1/2 times, well, we have 2 springs times x spring squared. And so now we need kinematics. So x spring is equal to what?
Should be the same,
R theta? Because that's always true. What's R equal to? No, it's not 20.
Oh, it's,
Point of
it's,
interest.
10 because it's from the line.
This point has 0 velocity. R is the distance from the point of 0 velocity to
It's 10 still.
the point of interest.
It's the same.
And so it's 20 minus 10. So it's 10 cm times theta. But what's theta? So x over 10. This distance is 20, half of 40. This distance is 10. Yeah, that was a sneaky one. That was a 1-point mistake. It's not a serious mistake, but it's something. So again, it's 40 over 2 minus 20 over 2. So basically, oh, that makes it easy. Right, so x equivalent, xs is equal to x. And so, hey, we can just cancel. And so k equivalent is 2k. What? Sure. Yeah, I got it like a few seconds after you said it. I assume omega n is square root of k over m. We don't need to do that. All right, here's another problem. Now we need to find the natural frequency and the damping ratio.
So we're allowed
What?
we're allowed to use J, M, and K, right?
If I didn't give you numbers, then that's what it is. Did I give you numbers? No. So then we're good. I know it bothers you to leave something in equations. No, we need a number. It's a mixture. All right. So, given this wonderful system here,
Oh, yeah.
Center is within a certain speed. So because we go the same distance from that.
what do we need to do?
Then this one right here, which has this one theta, this one has the same R, then the theta is the same. So they should, the spring should be compressing at the same speed as the object's roll. It's super tricky though, because I want to roll.
So how do we move springs? How do we find an equivalent spring? How do we move it?
How do we?
Series, parallel, or equivalent potential energy. How do we move mass? energy? How do we move damping?
Equivalence.
Equivalent what? Equivalent C is how?
That's a great question. Is it also?
Same way, right?
Same way, but it's equivalent. Not potential. What is a damper? Purpose of a damper.
Take energy.
Take away energy, which is rate of taking away energy or adding energy. Power. So we can use equivalent power to move a C. Or if you forget that, then
Then you look at your notes.
you look at your notes.
Good, that's not good.
Or we just call that point X equivalent. So if we move the mass in the spring to the top of the rod, then we don't have to move the damper. All right, so 1/2 m equivalent x equivalent dot squared is equal to 1/2 what?
K equivalent.
Oh, hopefully not. This is this is velocity mv squared. And so, what is the kinetic energy for the run?
1/2
So there's two options: 1/2 mass of the center of gravity times the velocity of the center of gravity squared, plus 1/2 j center of gravity theta dot squared. Or if you have a fixed point, it's 1/2 j about that fixed point
To the center.
theta dot squared.
Yep.
And so since I gave you the j about that fixed point, we can go with that one. Plus, bless you. Oh, was it a full bless you or? Plus, all right, so what's left? That block on the bottom, so it's 1/2 m x m dot squared. So that's the fundamental equation. And then now we need to use kinematics to relate our distances. So x equivalent, how we relate x equivalent to theta?
R theta.
Very good.
Nice.
And what is r in this case? 0.2. All right, and then what's xm?
R theta.
Yay!
0.4.
0.4 theta. Right, so this point has 0 velocity. This is the distance. The string is not getting any longer, so the velocity here is equal to the velocity here. And so we can write things, so we basically have 1/2 m equivalent, 0.2 theta squared is equal to 1/2 j in, and this should be dot theta dot squared plus 1/2 m 0.4 theta dot squared. Happiness?
Can you explain we got the 0.2? Which 0.2 is that?
So this is x equivalent. So x equivalent is 0.2 meters away from the point of 0 velocity. X mass is 0.4 meters away from the point of 0 velocity. And those are all theta dots because it's mass times velocity squared. So we have the relationship. We can take the derivative and go from there. All right, I'll assume we can do that. I'll assume you can do algebra because I'd rather get to the next problem rather than doing a bunch of algebra. So 1/2 k equivalent x equivalent squared is equal to what? 2k, 1/2, 2k, xs squared, which happens to be the same as xm squared. Now C has nothing to do with,
Oh, yeah, that's right.
are we done? Yes is the wrong answer.
How does the potential energy in the rod is what?
Right? We have a rod that's acting like a pendulum. Right, so this rod, the center of gravity is down here, and so it'll act like a pendulum. Pendulum?
Thank you.
So we have plus mass of the rod G times H. So we have an mgh term in terms of our potential energy. And then what is H equal to? No. No. It's the distance from the pendulum to the center of gravity. Oh, shoot. 0.1. So the center of gravity is down here at 0.1 meters below the fixed point. So again, this pendulum goes to the center of gravity, not the total length down here. And so it's L 1 minus cosine theta. So it's always L 1 minus cosine theta unless it's inverted, then it's 1 plus. And so in this case, L is 0.1 meters. 1 minus, what do we do with the cosine theta? It's not theta. No, it's cosine theta. This is L, this is L. This height here is L cosine theta. So this height here is L 1 minus cosine theta. We use the Taylor series expansion.
No.
Oh yes.
Theta squared over 2.
It's 1 minus theta squared over 2. And so this is 0.1 theta squared over 2. So we can plug things in. We have 1/2 k equivalent. What's x equivalent? 0.2 theta is equal to 1/2 2k x spring. Theta. Right, the spring is at the same level as the mass. Squared plus mass of the rod G 0.1 theta squared over 2. Yes. That is H. And so again, whenever you have a pendulum, you have an L 1 minus cosine theta squared theta term, cosine theta, Taylor series expansion is 1 minus theta squared over 2. And so we end up nicely with a theta squared over 2, which goes with a theta squared. Okay.
And the 1/2.
and the half. And so algebra. And then omega n is,
K equivalent.
and zeta is that, what's the equivalent going to be? C, because we moved everything to where the damper was, C equivalent is C. So it's usually best to move everything to one place. And since we didn't have anything that was nice, because we had the pendulum effect, that moving everything to where your damper was the easiest way to solve this problem. 1, 2, 3, 4. All right, this is, what type of system is this? Is what? A complicated system, but you had a homework problem similar to this. And the cart system is also similar to this, except for instead of a C here, we have a K here. So how do we go about finding the equations of motion for this? We basically did a free body diagram. So what are our forces on our,
In which direction do you want to do first?
how about on the top, forces? So a vertical force of
CX prime.
Cx dot, not prime.
Yeah, come on.
Prime is the spatial derivative, which we're not dealing with yet.
And Polish
Come on, Jerry. Come on.
And over here we have
KX.
Kx.
And then you have
C
Y
C
dot minus X dot.
Y dot minus X dot. So you have Y dot moving down. It's going to cause this to be stretching, so you have a force going down. If Y is fixed, then as X moves down, the force is going to be up, which is in the opposite direction of down. And so then we basically have the sum of the forces down is positive. What do we call down equals positive? Because we assumed X is positive going down. So then it's M times X double dot. That's equal to what?
All that added up.
All that added up, and so we have minus C times X dot minus K times X, because these are up, down is positive, plus C times Y dot minus X dot. So far, so good. What do we do next?
Make it equal to 0.
Not make it equal to 0. Right, we put all of our outputs on one side, all of our inputs on the other side. And so we get mx double dot plus 2cx dot plus kx equals cy dot. And what are we given?
We're given X.
We're given y. Y is 0.1 sine 4t. So y dot is 0.4 cosine 4t. And now we say, hey, that's like standard form. Right, we have a cosine omega t. Question? Answer? This is F equivalent. This is K equivalent. This is C equivalent, and this is equivalent. So what is the question? We want to turn in the amplitude of X. So what do we know for force vibration? We know that the magnitude of X equals F naught over K minus, the square root of K minus M omega squared plus 2 C, no,
C omega squared.
plus C omega squared, or we know that X over delta static equals 1 over 1 minus R squared plus 2 squiggle R squared square root. So which one do we want to do? The left one, because we know K, we know M, we know C. And so this is pho. What's pho? Measurable forest. 0.4 C. Oh, C is 1. Hey. So 0.4 times 1 over the square root. What's K? 9 minus mass 1 omega. No. Omega is the frequency of our force, which is 4. Omega n is a system property. Omega is an external input property. And so it's 1 minus 4 squared plus C. Oh, C is 1. Omega 4 squared. So yeah, I hear. So we were given y is 0.1 sine of 4t. So y dot is 0.4 cosine 4. Yes. Thank you. So this is C equivalent, M equivalent, K equivalent, and so this is 2 times 1. Which is C equivalent. Thank you.
Right, F naught is the 0.4 times.
F naught is C times 0.4. And that's going to be a number. Okay. It worked. We did do a couple calculations, but we got through everything. Questions? Answers? Enough? Not multiple choice. So, I mean, I could have lots of short problems, or I could have one long problem with 12 parts, or
Some problems are gonna like look similar to like this style. All
perhaps.
these.
It might look, so I would look at your homework. So it might look like something like your homework, or it might look something like this. There will be a problem like that first one. I can tell you that, because we're looking at differential equations solutions.
Do the PowerPoint slides count as notes? Like, can we-
They do, if you have the book.
Yeah.
Yeah, so this whole
So if you have the book, you can use my PowerPoint slides. But if you don't have the book, then you didn't pay for the privilege of all that information. You open a little book.
Because I have a previous version of the older book.
You can use it, but that doesn't match the notes on.
Well, it's like the equations you will
Okay, you can use that. You can use the Strong's outline vibrations. If you want that. You know what Strong's outline, or is that blank look? Strong's outline. That's Strong's. You're a genius.
I'm moving Y in this fashion.
Whatever is in front of the
Y
printer.
Y dot is
Whatever is in front of the
Just take your book.
So I did post solutions, except for maybe one Excel problem. There's no Excel or anything.
That's too bad.
No, because we're not learning anything. No, we're not learning anything new. No, I said actually on the homework, this is due next week. I remember.
Thank you.
Oh, man. Recording all the exciting